Dear students, today's topic is the photoelectric effect, which is when light electromagnetic radiation falls on a metal strip, then due to the interaction with this radiation and matter, the interaction of this radiation with this matter ejects some electrons. These electrons are known as photoelectrons. This is a metal surface and the electrons came out of the surface due to the effect of light is the electrons are known as photoelectrons. And the important thing is that every electromagnetic radiation is not capable of ejecting photoelectrons. The electromagnetic radiation must have some appropriate wavelength or below the wavelength. The most famous photoelectric experimental setup was due to Leonard. This is a diagram of the Leonard's experiment, and there is a description I have given here. This main tube, you look, this is the main tube. This one is the main tube, and this tube is the is evacuated. That means vacuum, there is nothing, almost nothing. The pressure is very low within the main tube, and this tube, within this tube there is a metal plate C. This one is the metal plate C here, metal plate C here, you see. Another plate is A here, you see, and another plate is D here. These A, C and D are held parallel to each other. Now you must understand that all these plates, as I have written here, actually A is the plate which is parallel to the plate C, and the plate C is placed at connected to a battery, and the C part is connected to the negative terminal of the battery. Therefore, and A part is connected towards either a positive terminal or zero potential. That means here it is earthing. This part shows earthing. So the potential of A, the A is definitely higher than potential of C. As I see, this is written in a wrong way, so do a correction here. This is incorrect. This is VC less than VA. Do a correction here. Note. And there is a, this will be VC less than VA. VC less VA. VA. Note it and make the correction instead of this place. VC is less than VA because VC is connected to the negative terminal and A is connected to either positive terminal or earthed. That means A is kept at zero potential. So VA is greater than VC. And there is a hole in the middle of A, so that here, so that if some particles are emitted from C, some of them pass through A, and this is done because of because of the need of collimating to make the flow of particles kind of linear. And this is kind of a focusing arrangement actually in a very elementary way. Otherwise there is no direct need of this plate and this hole. Anyway, some particles, charged particles who come out of this plate, they pass through the hole of A and go to D, and from D they are collected and put into a circuit which is not shown here, and a current is generated. And this side tube G, this side tube, this is the side tube G, from where electromagnetic radiation, it is written UV ray here, pass through it and falls on the plate C, and thus the photoelectrons are ejected, and they go to A, then pass to D. And there is a magnetic field which is actually put along, in fact perpendicular to the plane of the paper actually. Some magnetic field is placed there. Now the motion of the electrons along this way, motion of the charged particles along this way, and the field is perpendicular to the plane of the paper. So another plate E is set here. Plate E, actually this is the letter E, this is actually the plate E. Another E plate is here. This plate collects the electrons when the magnetic field is on. So when the magnetic field is on, all the electrons go to this plate and are collected there, and then put into a circuit which is again not shown here. So it is written at the end, the negative emitted particles are attracted to A, and part of them passes through the hole to reach D, so that a feeble current grows, and the magnetic field is set perpendicular to the plane of paper. Thus the negative particles bend. Note that there will be Lorentz force, that is why they will bend, and are collected by the plate E. The current is recorded again. Now if the potential between C and A, that means the potential between these two plates are V, and if the charge of the negative electrons in E, then kinetic energy is half mv square. Then you know half mv square equal to EV. This is an important relation. Another important relation is that if you consider that the path of the electrons are bent here, so there is a radius of curvature here. So if the radius of curvature is r, then definitely mv square by r is the centrifugal force on the electrons, which must be equal to B into E into V. From using these two relations, this one and this one, just you calculate V from here, and cancel this V by this V, and then put it there. So you obtain a relation E by M equal to 2V by B square R square. Now you measure the V potential that you apply from the battery. From the battery you know the V potential, and you measure the R from the trajectory of the electron, and you know the field strength B. So you know E by M, and this E by M result confirms that the negative particles are electrons. Remember that if the particles were positive, then the bend should be in this way. Then for positive particles, the bend should be along this direction. So direction will decide whether the particles are negative or positive, and now from the direction of bend you get the charge negative, and by E by M you are now confirm that these particles are electron. Now let us assume that this battery is now connected in a reverse order, like battery is reversed. So the positive terminal is connected to C. Positive terminal is now connected to C. Okay. Now Vc is higher than Va. That means the electrons in the plate C, the photoelectrons who are to go out, they will be attracted by the positive potential C. Therefore the flow of electrons will be less. I repeat, in the previous case this plate was in negative potential and the electrons were also negative, so it was easy that electrons were emitted from this plate. Now if you reverse the bias and this C is connected to positive potential, then this C plate will now attract the electrons who are going to go out. That means the current will reduce. The number of electrons emitted will become less and the current will also become less, and at certain value of the, if you increase the bias, the voltage of this battery, then at certain value of the voltage the current will stop, which is known as the stopping potential. Now then just when the current just stops, then E into Vs, if Vs is the stopping potential, will definitely will be equal to half mv square, that is the kinetic energy of the electrons. Now some observations regarding the photoelectric experiment due to Leonard. These were the observations. Most important things, that if the intensity is increased and the wavelength is not changed, then the no current will flow. No current will flow when the applied voltage is Vs. Remember it. The applied voltage is Vs. Now the intensity is increased. You are putting more light through the side tube G. You are putting more light through this side tube G on C. Intensity is increasing in that way, but still there is no current flow. Second thing is that if the wavelength is reduced, that means frequency is increased, no matter what the intensity is, that means you change the light actually. Initially say you are using red light, now you are using say green light or blue light, where the wavelength is reduced, then the current flow starts below certain value of lambda. That means initially the wavelength was high and you see no current is flowing. Ignore the stopping potential part here. Say it is in regular bias actually. That means when C is connected in a negative terminal. This part, for this part, go to the previous original picture. C is connected to negative terminal. Now your wavelength is say high, that is say red light, and you see that no current is flowing. That means no photoelectrons are emitted, and you now reduce the wavelength, and you just see that just below certain value of lambda the current will start flowing, and if you now want to stop the current, you have to reverse the battery and then you employ the stopping potential. From there you know how much what is the lambda and what will be the stopping potential. If you check the lambda is lowered, then the stopping potential increases. It means if lambda increases, photocurrent increases. In other words, the photocurrent after saturation, at saturation value, definitely does not depend on, we will discuss it later in detail, but this was the observation that the photocurrent after saturation does not depend on wavelength but depends on intensity. Note that whether the current will flow or not, it depends on wavelength or frequency. But if it flows, then the amount of current will not depend on wavelength but will depend on frequency. Whether it will flow is decided by wavelength. Whether there will be photoelectrons ejected, it will be decided by wavelength, and if there are photoelectrons, then the amount of photocurrent will be decided by the intensity of incident light. You will see, we will also discuss it later. And the features of photoelectron emission are listed here, that these are kind of a summary. and some additional observation, that is the rate of emission of photoelectrons. That is the photocurrent. This is photoelectrons. They are proportional to intensity. That means photocurrent is proportional to intensity and independent of wavelength of incident radiation definitely. And the velocity, that v, small v, and the energy, that means half mv square of photoelectrons vary from 0 to maximum. Say you are applying some wavelength which is capable of ejecting photoelectrons. Now, if if you use the stopping potential at that point of time, the velocity of electron is minimum, say 0. But if you do not use the stopping potential, instead you change the lambda actually, and then the photoelectrons will have certain velocity. So the velocities of photoelectrons vary from 0 to a maximum. The fraction of photoelectrons having a particular velocity is independent of intensity. You cannot increase the velocity of a photoelectron by putting more amount of energy on the plate. And the maximum velocity depends on frequency of incident light, and it increases if frequency increases. Definitely independent of intensity. For each metal there is a threshold frequency. I have written it as nu 0. Threshold frequency means threshold wavelength also. C by lambda 0 will be the threshold wavelength, below which no incident ray is capable of producing the photoelectric effect. That means your incident light, if your incident light, the frequency lies below nu 0, then there will be no photoelectron emission. That means no photo current, there will be no photoelectric effect. So your incident energy must have the wavelength greater than nu 0, and the process is instantaneous. Note in nu 0, note that nu 0 varies from metal to metal, and this process, the photoelectric effect process, is instantaneous. And if tau is the time between incidence of light and emission of photoelectrons, then tau is less than 10 to the power minus 8 second. And these features, as it was these were experimental facts, the people tried to develop the theory behind it. And at that point of time, the known theory was Newton's law, classical electrodynamics like Maxwell's laws, etc. And people failed to explain the classical, through classical theory, people failed to explain the photoelectric effect. What are the features? People failed to explain the intensity independence of the energy of photoelectrons. That means from energy conservation, if you think that if I put more energy, then this energy will be converted to the kinetic energy of electrons. But this explanation did not work in case of photoelectric effect, because say yellow light is not capable of ejecting any electron from the surface. Now you are putting more yellow light, intense yellow light, and this will still there will be no photocurrent, and this is unexplainable through classical theory. Similarly, the classical theory fails to explain the frequency dependence of the velocity. That means as I have written it here, that Vm depends on the frequency, increases if frequency increases, and Vm is independent of intensity. The maximum velocity increases with frequency increases. So this frequency dependence of the velocity of photoelectrons and therefore the existence of threshold frequency. Why no electron is emitted when the frequency of incident light is below certain level? Similarly, it fails to explain the instantaneous nature of the process. The classical theory shows very high time. In some cases, I have not found the value, but I learned that maybe more days, some more days or some more months, and some months are needed, some days are needed if you want to explain it through classical theory, that light should fall on a metal plate for some days or months, and all the energies are now then absorbed by the metal. This energy will go to the electrons, all the electrons will share those energy and they will come out. This time was so how, so it failed to explain the instantaneous nature. Similarly, it failed to explain the photocurrent to be intensity dependent. As I said, once the current is flowing, that means the energy, the frequency is above the threshold, then photocurrent will start flowing, and then this photocurrent will increase if the intensity increases. This feature was also not explained by using the classical theory, and it was obvious that a new theory is needed. So the explanation of photoelectric effect came from Einstein's theory. Einstein used the concept of Max Planck. There was a difference in, you note that Max Planck actually considered that in case of his theory for black body radiation, that the oscillation of dipoles, molecular dipoles, they were quantized, and the oscillation cannot take place in any frequency. Einstein used the concept and extrapolated it in case of electromagnetic radiation, and he said that the radiation is emitted or absorbed in discrete quanta. This quantum of energy is called photons, and energy of a photon is proportional to the frequency, E proportional to nu or E equal to h nu, where h would be the Planck's constant. It will come out to be like this. A photon travels with the speed of light, and the quantum of energy contained in a photon can be transferred, that means can be absorbed by some matter or can be emitted from some matter in full. Whole quanta will be absorbed or emitted, no fractional transfer of energy of a photon. That means if a photon has E amount of energy, then no half E or 1.3 E or 0.12 E or 1 by root 2 E is allowed. Whether it will be absorbed as E or it will not be absorbed, whether it will be emitted as E, the total energy, or it will not be emitted. Now, it is known that a certain minimum energy is needed to just release a photoelectron from the metal surface. The threshold energy, the threshold frequency we saw there, which threshold frequency means it was related to that particular radiation falling on the surface. So the energy of that incident radiation is the minimum energy known as the work function and denoted by the symbol phi. Phi is here denoted as the work function. This term is important, you have to understand it clearly. Work function is denoted as phi. So if h nu is the incident energy and phi is the work function, then the difference between them will be converted to the kinetic energy of photoelectrons. And if there is, we consider that there is no loss of energy in any sense. This is an ideal calculation, and by making the tube, photoelectric tube, very good vacuum inside it, you can achieve this part actually, that the difference of this energy is converted to the kinetic energy of the photoelectrons. Now, as you saw, when the electrons are just released, then the velocity is 0. Just released means they are just removed from the surface. So at that point, they have no kinetic energy to go from the plate C, the leftmost plate, to plate A. Look at the picture here. They are just released, but they do not move. So you write h nu 0 equal to phi, and by setting 0 here and writing nu 0 here. So your relation is that half mv square is h into nu minus nu naught, and it shows that kinetic energy, the maximum value of kinetic energy, depends on the frequency. And it also shows that no emission of photoelectron is possible if nu is less than nu 0. If nu is less than nu 0, then there will be a negative kinetic energy, which is meaningless actually. That means there will be no emission. Emission is possible only when nu equal to nu 0, which relates to the work function. And if you now increase nu, when nu is greater than nu 0, as you see here, for nu greater than nu 0, now photoelectrons are emitted. And if now you increase the intensity, that means you put more light with frequency nu, which is greater than nu 0, the number of photons incident on it increases, and in this way the number of photoelectrons, that is photocurrent, increases, and it is independent of then it is independent of frequency. If that means if you increase this nu again, then this photocurrent will not increase. That is the point. We now see the features in a graphical manner, and we will conclude our lecture. And that photocurrent versus potential we plot here. In the I is the photocurrent, V is the potential. Potential is the potential of the battery, B in the first page, as we see here. Potential of this battery V, and the photocurrent we collect from E, maybe from D also, from where we collect the photocurrent. Now the first one, the V and I we plot. Now you see, say your light is capable of producing photocurrent, and you will see it. If you increase the intensity, then the current will increase. So if you now want to stop the current, you will try to decrease the potential and take it to the negative direction, so that current is decreased, and at certain point the amount of current is 0. This is the stopping potential from O to V. Here the battery is in reverse bias, just remember. But whatever be the intensity, you see that if the frequency of the light is not changing, then all the curves, they merge at the same point. That means the stopping potential is same, and it depends on the frequency. It will change if the frequency changes, we will see it later, but it has no relation with the intensity. So photocurrent depends on intensity if the frequency is capable of creating photocurrent. It is conditional, remember it. The second thing is that photocurrent versus potential at different frequencies. Now you change the frequency, but your intensity of radiation remains unchanged. Same intensity, but your frequency changes. You see that now in this case we have considered the frequencies, all are capable of creating photocurrent. All are capable of creating photocurrent. But you see that for certain frequency nu 1, the current grows this way and then saturates. For nu 2, this is the path, and nu 3 current grows this way and then saturates. Look at the picture from a good book so that you get the actual presentation of the curves. With the third one is almost okay. But the nature is clear from this picture, and you see all the frequencies are capable of creating photocurrent. And after, when the current saturates, initially the current increases because the flow of electrons rather the reserve of electrons on the metal surface are getting energies from the incident wave, and now start flowing. And when all metals start flowing, the photocurrent saturates. So when it saturates, you see that you cannot say that this is due to nu 1 or nu 2 or nu 3. So photocurrent in its saturation region does not depend on frequency. And if you now want to stop this current, I have missed the current I here. This is the photocurrent I. This direction is the photocurrent I. You see that if you now want to reduce the current, and this way, along this axis, it will be V, as in the previous case actually. Same here, I and V. And now you reduce the potential, and from after O you go to the reverse bias. That means you change the polarity, you reverse the battery. The positive end now is connected to the C plate. Now and then you go on increasing. At for frequency 1, you see that at Vs1 is the stopping potential, because frequency 1 is the minimum one, and stopping potential will also be minimum. And if you increase the frequency, the stopping potential will also become more negative. And by using the concept of stopping potential, we can see that half mv square will be equal to E into Vs, because this energy stops. This energy is same to the kinetic energy, because if there is no electron, the electrons are there to be emitted from the surface, as the incident radiation is there on the plate. So electrons want to go out, and they have certain energy. Now you are not allowing those electrons to go out, and for that you are putting more energy to stop the electrons through the battery. So if no electron is going out, then these two must be same. So half mvm square equal to E into Vs, where S is the stopping potential, and now equate it to the Einstein's equation, and you see that Vs you can write as H by small e into nu, and so this will be Vs will be 1 by E into half mv square, that is 1 by E into kinetic energy. You plot it along the y-axis, and you plot the frequency along the x-axis. So you plot stopping potential along y-axis and frequency along x-axis, and then you get a straight line here. You get y equal to m into x plus c. This is your y, this is your equal to x, m into x, this is equals m, and this nu is x, y equal to mx, plus c in this case here, plus I will write it as minus c. The constant I will change, y equal to mx plus c. This screen, this pen or the ruler on the screen cannot write continuously. So y, this is equation of straight line, this is our y, and nu is compared to x, then m must be the slope must be equal to h by e, and this part is 1 by e into phi, because if you set y equal to 0, then x equal to this part phi by e. If you set stopping potential, you see, and the stopping potential is 0, and that means nu equal to this part. Yes, Vs equal to 0 at this point. No, at this point nu equal to 0, so Vs equal to minus phi by e, so this part in the negative direction, nu equal to 0 here. So hence, using the photoelectric effect, you can evaluate also the value of the Planck constant, measure the slope of the curve, and use the charge of the electron, and from this way you yield the you calculate the Planck constant. So we stop here.